Welcome everyone to a brief overview of lesson 2.1 from calculus, which is all about average versus instantaneous rates of change. So let's start with the average, something that we're a little bit more familiar with. If I look at this blue line here, it's written in point slope form. So the point we're using is a comma f of a, and the slope is taken from the difference in the y values of 2 points over the difference in the x values of those 2 points. So y2 minus y1 over x2 minus x1, or f of x1 minus f of x2 over x1 minus x2. Change in y or the change in x, rise or run. That's slope. That's what average rate of change is. It's the average slope between 2 points. And for lines, they're constant. So the rate of change of this blue line is constant. In this case, it's negative. And we could figure it out if we wanted to, but it really doesn't matter. What does matter, though, is this nice orange line. And the blue line is called a secant line because it intersects the graph twice, or at least twice. The orange line is called a tangent line because it intersects once, only at this one point here. So I guess the question is, how do we make the secant line into the tangent line? How do we take this average rate of change into something that would be the instantaneous rate of change? Because if it only touches once, then that's the instantaneous rate of change of the graph at that point. So if I take this b value and I make it closer and closer to the a value, you'll notice that the lines get closer and closer together until they seemingly overlap, right? But if I hide the orange line here, the secant line went away. Why is that? Well, we divide by 0. We get 0 in the numerator, and we get 0 in the denominator, so it can't calculate the slope, therefore it can't compute what the secant line would be there. So how do we overcome this obstacle of the a's and the b values needing to be the same for us to have this tangent line? How do we have a difference between them being 0? And that's where we use a clever math trick. What we've learned through the entirety of Unit 1, we're going to use some limits. So I'll be right back, and we're going to talk about how to use limits to find the instantaneous rate of change. Welcome back. Here are the formulas for the average versus the instantaneous rates of change. And if we notice, the average and the instantaneous rates of change look very, very similar. The major difference is that the instantaneous has a limit. Now, these formulas might look like they came out of nowhere. I used B and A when it came to the examples I showed you before. So in this case here, B would be defined as the A value plus some H. H is just the difference between where the A is and where the B is. So in this case, if A was 1 and B was 2, then H would be 1 as well. And that is how you would find it. You have the f of x1 minus f of x2 over x1 minus x2. Here is the same kind of approach. The difference is that H value, the difference between the A and the B, is approaching 0, is getting smaller and smaller and smaller, infinitesimally small. What happens is that the f of a plus h here and the f of a get really, really close. And the bottom is just h. Well, if we simplify this out, we would just subtract the a values and those would cancel. So that's where this h comes from. And these formulas here are simply the f of x1 minus the f of x2 over x1 minus x2. For both of them, the major difference here is that we're just saying that the x is getting closer and closer to a. So those are the formulas. Let's talk about using one of them. So let's do an example using what I showed you in a previous part. This f of x is equal to x squared minus 1, and we're going to do it at the point x equals 1. So what we're going to do is we are going to use this fancy formula here. A is what this x is equal to, and h is some h that we're trying to get to approach 0. So right now it's just a variable. Hopefully it'll cancel out later on. So let's evaluate this, shall we? The limit as h approaches 0. And we're going to first input this 1 plus h. So that would be 1 plus h squared minus 1, and then we're going to subtract just evaluating the function at 1, which would be 1 squared minus 1. And we're going to put that all over h. So let's clean this up a little bit. Well, we know that 1 squared is 1, and 1 minus 1 is 0, so this entire piece just goes away. This is a square. It's something we're going to have to distribute out. So that distributes to 1 plus 2h plus h squared minus 1 for this minus 1 over here, and then minus 0 because that is what the result of evaluating it at 1 was. All over h, and you might see where some magic is going to happen. Well, if we look closely, the 0 doesn't matter. We have a positive 1 and a negative 1. Those cancel. And that leaves us only with h's. We have the limit as h approaches 0 of 2h plus h squared over h, which means that we can eliminate an h from every single term in the numerator and denominator. Get rid of that h. We can get rid of one of the h's in the h squared, and get rid of the h in the denominator. Again, we're using division, so it doesn't go away, it just turns into a 1. And that will leave us with the limit as h approaches 0 of 2 plus h. And if we evaluate this limit now as h approaches 0, we get 2. So that is the instantaneous slope of this function at 1. Back at the graph here, we can see that if the a value is indeed 1, that the tangent line has a slope of rise 2 to the right 1. It has a slope of 2, and that's what that process pretty much means. So we're using the same formula that we kind of have been. This y2 minus y1 over x2 minus x1, we're just making the difference between the x2 and the x1 negligible, infinitesimally close. That is it for 2.1. I hope to see you in the next video.